grams of sulfur and 4.5 grams of oxygen. What is the empirical formula? How many of you have tried it?
I tried it, and then on my PowerPoint it didn't say like the 2.26 what element.
I thought it was sodium, I guess, because it's in the same.
No, 3.24 grams is sodium. 2.26 grams is sulfur.
Oh, it
In my
wasn't on it.
PowerPoint, in my PowerPoint it didn't say something.
It didn't say nothing,
Oh,
so I just used the sodium. I just calculated the sodium.
well, it should be sulfur. Maybe some mistake. Okay, you can put sulfur on it. Okay. If you don't have it, it should be sulfur. I'm updating it now. Okay, it's sulfur. Now, okay, well, tell me the way how we solve the problem. What's the first thing that we need to do? Hand. What's the first thing that you need to do? You have this problem right here. What do you do? Okay. Who can help hand? Tarek.
I don't believe.
Okay. Milton? No. Brandy?
I don't know.
Yeah, what's the first thing that you need to do?
Well,
Get the total mass of the compound. Add all the masses together.
Why do we need to ask?
I didn't do that. I didn't do that.
Okay, go ahead. What's that you need to do?
I multiply 3.24 times 1 mole of sodium over 23.
Oh, okay, good.
Over
Good.
23 grams of sodium, and I got 0.1.
You divide it. You in other words, Anit, what you did is
I
you
divide-
convert the gram to moles.
Yeah.
Good.
And
Okay.
then from there, I find the empirical formula.
The things that we need to do is we have been given grams. Please listen carefully. We have been given grams, okay? 3.24 grams sodium, 2.26 grams of sulfur, 4.51 grams of oxygen. It was given to you, okay? Oxygen. Oh, right here. Okay. This oxygen,
I know that.
this sulfur,
Oxygen.
and we have sodium. The very first thing we need to do is we have to divide each amount by their respective atomic weights.
But do that, like when you look at it, do that make sense? I thought oxygen was like the air though. Like you can't.
Oxygen is what?
I thought oxygen was like the air.
Oxygen
The
is
air. Like,
the air.
right.
Yeah.
So you got grams of air.
Yes, of course.
I ain't gonna get that.
Oh yeah. No, listen. Are you in my lab class? You are in my lab class, right? What was the purpose of experiment 5? Have you done? I'll remind you.
Oh, I think.
Now we did magnesium oxide in reaction, right? Do you remember that? We did the empirical formula of magnesium oxide, right? Now here is my question for you. How do you determine the amount of oxygen?
Oh yeah, you gotta get rid of that.
Do you understand?
Yeah, I
You
get it.
determine the amount of oxygen by subtracting the mass of magnesium,
Right.
the original mass of magnesium,
The mass of
from
magnesium oxide.
from the burning mass of magnesium. Burning.
Alright.
Burned magnesium. That means if it is burned, there is oxygen there. Okay? So you subtract. So yeah. So the very first thing that you need to do is you need to divide each amount by their respective atomic weights. Is that clear? You need to divide each amount by their respective atomic weight. That means, and it started here, she said 3.24 divided by 23. That's one step. We continue. 2.26 divided by 32, because the weight of sulfur is 32. And then 4.51 divided by 16. We divide by the respective. Dividing, in a sense, gives you what? More. It gives you more. Now, how many moles you have? 3. You have 3 moles. You have 3 moles. From the 3 moles, we have to pick the smallest one. Okay? I don't know. Now tell me, when you divide 3.24 by 23, Anis, what did you get?
0.098, that's the smallest one.
Okay, wait, I don't know. I don't know. 0.098. Write that down, okay?
Yeah, but I didn't do sulfur because I thought it was sodium.
Okay, let's do now. Let's do now. 2.26 divided by 32. Can anybody tell me what's the answer?
0.07.
0.07. Please write this
So
value,
that's
everybody.
the smallest one then.
We don't know yet. Let's finish. We have to finish with oxygen too.
Second
You
person.
said 2.26 divided by 32.
Sodium is
Is that what you said?
0.14%.
Okay, everybody, I want you to write the numerical value for sodium. 3.24 divided by 23, what do you get?
0.14.
0.14. Write that down. Is that right?
Yeah.
Okay, write that down. 0.14. Everybody, write that down. 2.26 divided by 32, what do you get?
0.07.
0.07. Is that okay?
32.
32. You agree?
Yeah.
0.07? Agree, everybody? Okay, let's continue. 4.51 divided by 60.
0.28.
0.28.
.28.
Well, it doesn't matter, 0.28 or 0.28. Let's wait. Let's do step by step. Is that right? Let's do step by step, okay? How many more ratios we have? 3 more ratios. Which one is the smallest one?
Second one.
The
Sulfur.
second.
Sulfur.
0.07.
0.07. Okay? 0.07, that's the smallest one. Now what do we do with the smallest one? Divided each mole ratio by the smallest one. Divided each mole ratio by the smallest one. That means we have to divide it by 0.07. If you divide the first one, 2, you get 2, right? If you divide the second one, you get 1. If you divide the third one, you get 4. Right? That means these numbers are whole numbers. 1, 2, 4. These are whole numbers, right? That means, right? These are whole numbers. For sodium, you have 2. For sulfur, you have 1. For oxygen, you have 4. Right? These numbers are used as a subscript. Very good. These numbers are used as a subscript to write the empirical formula, which means the empirical formula should be, in this case, Na2SO4. SO4. Does it make sense? Is this the right formula? Yeah. When you make a composition of sodium ion with sulfate ion, theoretically, you should get Na2SO4. And Donna, what's the name of this compound? If it is a formula, it has a name, right?
Yeah.
If it is a formula, if it is real, it has a name. And the name should be? I'm sorry?
Sodium sulfate.
Sodium sulfate. What kind of formula is that? Ionic or molecular? Ionic. How do we know it's ionic? It has metal, which is sodium ion, and it has a non-metal, which is sulfate ion. Metal and non-metal. Make sense? Okay. Now, let's go to the third one. We have calculated the empirical formula of a compound that has 74% sodium and 26% oxygen. What's that you do? What's the first thing you need to do here?
You gotta change the percent to the gram.
You got to change the percent into grams. The easiest way, the convenient way that you should do is you got to convert the percent into gram. How you do this mathematically? Yes. If you are assuming the sample that you are working with is 100%, 100%, 74% of 100 is 74 grams. Because the sample that you are dealing with is 100%. 26% is 26 grams. So that makes things easier if you consider the sample that you work with is 100%. Okay? So 74% is like 74 grams. 26% is like 26 grams. Oh, by the way, before I forgot, we have an event today in Environmental Science Club. There's a fundraising, so they are selling donuts and they are selling coffee, I guess, too. So it's nearby the cafeteria. So please support them, okay? You don't have to do like donuts, muffins, or things like that. They sell muffins there. So that is support for the Environmental Science Club. So, you know, it is it's $1 or some, so they need your support. Okay? At least let's support them. I'm going to buy some muffins too. Okay? 74% is 74 grams. 26% is 26 grams, okay? So, okay, so once you have this, what's the next step? Divided by their atomic weight. That means you divide 74 by 23. You divide 26 by 16. If you divide 74 by 23, what do you get? 3 point? Okay. For sodium, you got 3.22. Okay. I'm sorry?
217 or 22.
Okay. Okay. For oxygen, if you divide, what do you get?
1.63625
1.63,
or 625.
625?
No, 1.63 or 1.625. If you
I
round
put
it.
1.63. Let me put 1.63. Now, this is a more ratio. How do I get that? I divide 74 by 23. How do I get this? I divide 26 by 16. Okay? What's the next step from here?
Divided by
Divided by
small
small
one.
one.
Pick the smallest number, which is the smallest one is 1.63. Divide this by 1.63 and you divide this by 1.63. And this gives you 2, this gives you 1. Whole number. So this number are used as
So,
a subscript, okay, to write the empirical formula. So the empirical formula finally will be what? Na2O. Does that make sense? That's the formula, right? What's the name of this?
Sodium oxide.
Sodium oxide. If someone say disodium oxide, does that make sense? If someone say disodium oxide, because there are 2 sodium here.
We don't have to say. It's only one.
Can we say disodium oxide? If you want. It's not if you want. Right? It's not if you want.
Is it that one?
Huh?
Is it?
I'm asking you. No, we can't. It's not molecular compound. It's ionic compound. When do you use di? When do you use tri? When do you use tetra? It's only for covalent compounds, not for ionic. Not for ionic. And we know that this is ionic. Ionic. So we're not going to say disodium oxide. We just say sodium oxide. The only compound that's formed is sodium oxide, period. There's no di, there's no tri.
I have a question.
Yes.
So can you say H2 is dihydrogen oxide?
You can say, but it's not common. It's not a common practice to say dihydrogen monoxide. Yeah, yes, they are. But water, at the same time, it's more polarized compound. It's like more ionic-like compound. Okay, so the nomenclature for water is dihydrogen monoxide, but the common name for water is water, H2O. Okay.
When you say Viacom's name,
Because this is ionic compound.
okay, all right. So you only use di, tri, all of that when it's
When it is molecular, when it is covalent compounds. Okay? Like N2O, for example. See N2O. What is the name of N2O? Dinitrogen monoxide. Because there's a possibility. This is sharing of electrons. Sharing means they share in many ways. So maybe there's trinitrogen. Maybe there's tetranitrogen. Okay? But in ionic compound, it is about transfer of electrons. Transfer of electrons from metal to non-metal. So there's only one compound existed.
So can we have like NaO?
NO?
NaO, like without the subscript to.
Well, no, we can't. We can't. NaO means that they're not balanced. Okay, if you say NaO, what's missing here? Okay, because oxygen has a charge of -2, sodium has a charge of +1. So we need to have one sodium to counterbalance with the charge of oxygen. So there's no way that you may have a combination, but it's not a compound.
So it's only possible different, I mean, different molecular form in the
Covalent compounds. In covalent compounds, yes, because takes the concept. The concept is covalent compound is formed by sharing of electrons. Sharing means there are many ways, there are many possibilities. Two compounds can form different compounds. I mean, two elements can form different compounds. Nitrogen and oxygen can form nitrogen monoxide, can form nitrogen dioxide, can form nitrogen trioxide, can form dinitrogen monoxide, because what is happening there, depending on the sharing of electrons, the transferring is directly from metal to non-metal, and the implication is that there is only one compound formed there. Okay? So we have another question here. Mercury forms a compound with chlorine. Again, the principle is the same. Okay? What's that we need to do? We have 73.9% of mercury. We need to get the molecular weight, the atomic weight of mercury. What is it? What is the atomic weight of mercury? Look on the periodic table.
200.59.
200.59. So we have to divide 73.9 by 200.59, right? And we go back to chlorine. What is the atomic weight of chlorine?
35.5.
35.5, right? If you look on the periodic table, it is 35.5. Yes. Okay, 35.5. So we divide 26.1 by 35. Okay, let's go on. We have, that's mercury and chlorine, right? When you divide 73.9 by its atomic weight, what do you get?
0.36.
0.36.
36.
0.36, okay. We have mercury here, we have chlorine here. The mole for mercury is 0.36. What's the mole for chlorine?
0.74.
0.74. Do you agree with these two values, everybody? You agree? Okay. So what's the next step, Randy? What do I go from here?
You take the lowest one.
I take the lowest one. Which one is the lowest one?
The 0.35.
0.36.
I mean, yeah.
0.36. So I divide everything by 0.36 because that's the lowest one. If I divide this, 1. If I divide this,
2.
2. So the formula should be what?
HgCl2.
HgCl2. Make sense?
Yes.
Okay. What's the name? I'm sorry?
Mercury 2 chloride.
Mercury 2 chloride, because mercury is again a transition element. Transition element. If you have transition element, always you have to indicate what? The Roman numerals, the charge. Okay, the charge of the mechanic element. Okay, now we discussed about empirical formula. Let's see molecular formula. The way that we calculate. By the way, before starting about molecular formula, let me ask you this question. What is important? What is the significance for us? Is it empirical formula or is it molecular formula? Can provide us more information? Molecular. So why we are wasting our time to study empirical formula? Why we need to know about empirical? Because molecular formula is the one that provides you the accurate number of atoms and molecules, right? That's molecular formula. But we are here spending time to dig or to explore about empirical formula. What's the purpose?
Because it shows as a simple expression.
Because to get molecular formula, you have to have empirical formula first. Okay? You have to have what is the smallest ratio, what is the proportion you have there. Okay? Empirical formula is the basic to get molecular formula. The final destination, the final goal is to get molecular formula, but you have to start with the empirical formula. Of course, once you get the molecular formula, the next step is going to be what? Structural formula. The structural formula tells you how the atoms are connected to each other, what is the central atom, what is the geometry, what is the angle between central atom and the adjacent atoms, all these informations, because we need to know these too. Sometimes the effectiveness of a compound even determined by the degree of the angles. If there is a little bit distortions in the angle, the effectiveness will be affected too. So you see, we have to go from simple to complex. Okay? We have to go from empirical formula, move to molecular formula. From molecular formula, we have to go to structural formula. So, what we have here is, once we know the empirical formula, we need the molecular weight to find the molecular formula. Okay? One more information is provided to calculate the molecular formula. The experimentally determined molecular weight must be given to you. Okay? In empirical formula, you don't need that information. In empirical formula, you just need what percentage or what amount are each element in a sample. What amount? Okay? That is it. Once you have the amount in a sample, then you calculate the mole ratio. Okay, you calculate the mole ratio. But in molecular formula, the person, your supervisor, or the chemist, or the analyst who ask you to determine the molecular formula must also provide you experimentally determined weight, molecular weight, that is needed to calculate the molecular formula. Okay, so. So that's the only difference between a molecular formula and empirical formula. Okay, maybe I can explain that in examples. We may have some examples here. Okay, here, experiments shows that a substance known as adipic acid is 49.31% carbon, 6.9% hydrogen, and 43.79% oxygen. Again, from a separate experiment, the molecular weight of the adipic acid is found to be this much, 146.144. Now, calculate what? Calculate the molecular formula of adipic acid from the data. Okay? So, we're going to start from empirical formula first. Okay. Can we calculate the empirical formula of this compound?
Yes.
Okay, how do we calculate the empirical formula?
Find the mole and the small one and divide by whatever.
Okay, let's do it together. Now, what is the atomic weight of carbon? 12. What is the atomic weight of hydrogen? 1. What is the atomic weight of oxygen? 16. Okay, I want you, everybody, divide carbon, which is 49.71% by 12. 6.9 by 1, and 43.79 by 60, and give me the answer. Okay? I want you to divide. Use your calculator or use it manually, whichever way is convenient for you. I want you to do that calculation. I also want, how many of you have access to the internet here? You have access to the internet, okay.
Right now, or whenever?
Right now, because there's something that we're going to compare our results from. I want you to make a Google and search for the right molecular formula of adipic acid. We're going to make here, and then we're going to compare our answer with the formula we have, or the formula that was on a Google search. It's adipic acid is a known compound, but we wanted to make sure, or we wanted to make a justification whether our formula is right or wrong. Okay, now, have you divided? How many of you have divided? Okay, how many of you still are working? Okay. 49.31% carbon. If you divide, what do you get? 4.09.
4.11.
4.11. Yes or no? Okay, what's the next number after 0? No. Yeah.
I got 4.
Yeah, that's what I got.
Yeah, 109.
4.109.
4.109?
1.11.
So we can say 4.11 is fine, okay? 6.9 divided by 1? 6.9. Right? 43.79 divided by 60?
2.74.
2.74. Okay, we have 3 more ratio. What's the next step? Divided by the lowest one, which is 2.74, 2.74, 2.74. Right? Now, if we divide 4.11 by 2.74, what do you get?
1.4.
You get 1.
1.5.
Okay, raise your hand.
1.5.
It's confusing me. Yes,
1.5.
1.5. Okay, now let me turn off this so that we can. Right? You got 1.5, right? How about here? 2.5. How about here? 1. Okay?
I think it's 2.4 instead of 2.5.
What's the next number you have?
2.41.
It's 2.5.
got 2.5.
2.51. 2.5.
Okay, I believe that should be 2.5. I'm not sure, but I believe. Okay, do one more time. Now, here is my point. That all of you need to pay attention. These are the numbers that we can't round in chemistry. We can't round in chemistry. We wanted to get the right formula. If you don't get the right formula, you're giving the wrong information to your patient, for example. And instead of curing him or her, maybe you kill your patient. So we don't want that, right? So now there's another way to find the right formula. Now some of you might say, 1.5 can be rounded too. Some of you might say, no, 1.5 is between 1 and 2, so I rather skip 0.5 and I can leave 1. But it's in between, do you understand? Or some of you say 2.5. No, I think 2.5, I would say 2. No, 2.5 has to be around this 3. Now 2.5 is a number, is exactly between 2 and 3, right? 1.5 is a number, it's exactly between 1 and 2. We can't play a game here. We can't play a game of numbers. Because this is formula, this is a chemical formula, this is a drug that we have to make here, right? So the best approach here is we have to find a number and multiply all numbers by the same constant numbers. Okay? By the same constant numbers. That doesn't make any difference. If you multiply one quantity by the same number, the product remains the same. So you can pick a number, smallest number.
2.
2 would be the smallest number. You multiply this by 2, you multiply this by 2, you multiply this by 2. What do you get?
3.
3,
5.
5, 2. Now this is good. This is a whole number. This can be used as a subscript. Why we multiply by 2? That's a good question. Who can answer that?
The smallest whole number that you multiply, I'll give you another whole number.
Okay. The reason why we multiply is that we cannot sure to round up this number. So we prefer to multiply to get whole number because formula, whatever formula we have, has a subscript, right? The subscript has to be whole number. You can't have a fraction of oxygen. You can't have 2.5 oxygen, right? Either it has to be 2, it has to be 3, it has to be 5, right? There's no like 1.5 sodium. It has to be 1 sodium or 2 sodium.
So you got the whole number from the smallest one.
Yes, if 2 is the smallest one. 2 is the smallest number. I'm sorry?
Because one won't make it.
Because one will not make it. 1 is the smallest number. Yeah. Because 1 times any number is always that number. 1 will not make it. So we have to go 2. Now, if 2 doesn't work, then we have to go 3. If 3 doesn't go, we have to go 2. If 4 doesn't go, Beverly, if 4 doesn't go,
No, I was just laughing at him.
okay, 4 doesn't go, where do we go?
5.
5. That's how it is.
I would have killed my bitch.
So here now, listen, that's why I'm asking you how many of you have an access for the internet, because we're going to do this and we're going to see whether we are on the right track or not. Okay? So C3H5 O2. We don't know whether this is right or wrong. We're going to check. That's why it was we actually adipic acid is a known formula. It's not something that we chemistry class students have created here. There must be a formula known as adipic acid, and it has to have a formula. And we have to compare our result from whatever is around or accepted by the scientific community. However, this is empirical or molecular? This is empirical. Our goal is from this empirical formula, we have to go to where? To molecular. Okay, this is our goal. Our goal is to, from the empirical formula, we have to go to the molecular formula. Molecular formula, this is our goal. Okay, now, what is the empirical weight? What is the empirical weight?
73.
73. The empirical weight is going to be 3 times 12, 5 times 1, 2 times 16, right? And you said 73. 73. 73 mu. Okay? That's 73 mu. Is that clear? Does that make sense?
Yes.
Okay. Now, in the problem, it was said that the the molecular weight was given to you. 106.
146.1.
The molecular formula is 146.
1 kilo weight.
The molecular weight, sorry. The molecular weight is 146.144
144.
mu. That was given, okay? So there is something called a factor N. There is something called a factor N. A factor N can be calculated as dividing the given molecular weight, the experimentally determined molecular weight, by the empirical weight. Okay, that's called a factor N, which means 146.144 divided by 73. 2. Okay?
What do you say factor N is?
The factor N is the ratio of the molecular weight, the experimentally determined or the given molecular weight, by its empirical weight. That's called the factor N. And the factor N is actually helps us to get into a molecular formula, okay? Which is, our empirical formula is C3H5O2 multiplied by N. It gives you molecular formula. Yes. It gives you molecular formula. So C3H5O2, what is our N? 2. So you multiply these 2 by the whole empirical formula, then you ended up with what? C6H10O4. This is a molecular formula. Now,
You got it right.
we got it right.
Yeah.
See? So we are right. So adipic acid has a formula C6H10O4. Right? Those of you who have internet, you prove that this is a formula for adipic acid. Yes.
So where 146.1?
That is given.
Oh.
That is given. When you are asked to calculate the molecular formula, again, the molecular weight has to be given. So what you need to do is you need to calculate the empirical formula. From the empirical formula, you need to calculate the empirical weight. Once you have the empirical weight, you divide the molecular weight by the empirical weight. That gives you n, factor n. This n is used to multiply the whole empirical formula, and finally you get what? Molecular formula. You get molecular formula. So, you know, this is one step. This is one step that you need to do. This one is steps that you need to do. Okay. There is okay, we have like 5 minutes, right? Can we do this problem here, please? As class working, make sure that I'd like to know whether you understood it. Find the empirical formula. How many of you got the empirical formula? What's the empirical formula?
CH3O.
The empirical formula that you get is CH3O. How many of you got CH3O? How many of you got, okay, most of you got CH3O, very good. Okay, now this is the empirical formula right here, right? And then from here we can determine the empirical weight. Okay, what is the empirical weight? It's going to be 31 AMU.
It's gonna be great.
But it's AMU.
Yeah.
It's AMU. Okay. Carbon is 12. Hydrogen is 1 times 3 is 3. Oxygen is 16. So 12 plus 3 plus 16, that gives you 31, right? Now we have the molecular, the determined molecular weight, which is 62.1, right? So N is going to be 62.1 divided by 31. That gives you 2.
But it doesn't matter like if it is AMU and during program.
It doesn't matter, it's a ratio actually. Where if this gram per gram will be cancelled, if this MU, it will be cancelled MU by MU. Okay, it really doesn't matter. What you need is the ratio 2 with no unit. There's no unit because the numerator and the denominator will be cancelled out. Okay, so we have CH3O times 2, right? And gives you C2. H6O2. Do we have that?
Yes.
Yeah.
See, we have our judge here.
You got it right.
You got right. Let me see. C2H6O2. That's the molecular mass is 62.7. The density is 1.13. The melting point, the boiling point, solubility in water, viscosity, etc., etc. So it is right. It's in glycol. So does that make sense?
Yeah.
So that's how we calculate empirical formula and molecular formula. We're going to continue next week, and I believe we have to finish this chapter by next week, chapter 3. And then maybe Friday, you may have an exam next Friday, chapter 3. Okay?
Just chapter 2.